Okay, so tonight by midnight you have homework due over section 6.3 and 6.4. Right? Don't forget that. Are there any questions over that material? Yes.
There was one question, and it was on section 6.4, and it was where you had to find to get a D, and it was like below or above 7%, and like below like 77.
It said you had to be above a certain amount and below a certain amount.
Yeah.
Okay. So to get a D in a class, it was a grades thing.
Yeah, but when I tried to do like the inverse normal thing, like all the other questions, it like did not give me the right answer.
Okay, so yeah, it might be a rounding thing.
There was like way off.
Okay, so if grades are normally distributed, and we can make up some values here, but a D would be, for my class, a D would be 0.6, right? Or 60%, so we'll call it a grade of 60, and between a 70, right? But they don't give you the mean and the standard deviation.
No, they did.
Okay. And then they say, what would the scores be to get a D?
Yeah. And then they gave you like, if to get a D, you had to get like above a 7% of the total of everybody, or below or something.
Okay. So let's make up numbers. Suppose we had a mean of 75 and a standard deviation of, I don't even know what a good standard deviation would be. You remember approximately what they were? 8.5, 9, okay. We'll call it 8.5 so that we don't have nice whole numbers. Right? So to get a D, the lower and upper bounds for a score of a D, right? So you need the value that has what percent below it.
It would say something like lower than the top 80% of the class and above the top 9% or the bottom 9% of the class.
Bottom how much percent?
Bottom 9% of the class.
Okay, so lower is above bottom 9%, and then the D goes to below the,
And then the upper was below the top 80% of the class.
oh, top 80%, right? Okay? So if we draw a picture, if we have a mean of 75 and we have a standard deviation of 8.5, then 75, let's scoot this over a little bit, 75 minus 8.5 would get me to 66.5, thank you. Right? Now look at these percentages. So 9% below L. Well, two standard deviations would be 2.5% below, right? So I know it's going to be up above that. This number has what percent below it? 16% by the empirical rule, right? So I know that my L is going to be somewhere in between 1 and 2 standard deviations. So we'll call it right there, right? So what I need is I need the 9th percentile. I'll just write it as P09. Okay? So L is equal to what? Using the inverse norm function. What do you enter? 0.09, 75, and 8.5. Okay? So while you're working on that, let's do the upper one. Below the top 80%. How do we work with top 80%? Yeah. Take 1 minus 0.8. They're having more fun than we are. Take 1 minus 0.8 to get 0.2. So upper will be inverse norm of 0.2, 75, 8.5. And that's the tricky part, is not putting 0.8 in there. You have to realize, oh, it's upper 80 means lower 20. The calculator wants the left area to the left, not the area to the right. Okay, so what's this top one? Everybody got a value? Everybody's waiting on the other guy to do it. 63 point what? 60. Okay, and then what about inverse norm of 0.2?
67.85.
67.85. So there's your range to get a D. If you score between a 63.6 and a 67.85, you're going to get a D in this class. Okay? It sounded like you were kind of giving her a hint about rounding.
It says you can round to a whole number if possible. I found that you have to use at least one decimal place for it to accept the answer.
Okay. Yeah, so.
No, mine was like, I would get an answer that was like 65 and the answer would be like 72, and it was like way off.
Way off, okay.
Yeah.
Well, I haven't remembered to say it, so this is a good time to say it, but this homework system in Hawks is not set up very well, I don't think, for allowing me to answer your questions while you're in there working on it. So I've practiced with a few students and it works well. Do you know how to take a screenshot? Okay? If you're looking at me like, what the heck is a screenshot? There's a either Control or Alt. Some computers it's one, some the other, so try them both. Alt, and then usually the upper right side of the keyboard is a print screen button. And it's usually not written on the key, but it's above the key, so that's why you hold the Alt button to get to that. And it'll be abbreviated like PRTSC or something like that, print screen. So Alt, print screen, and that puts the image of your screen into the buffer, the memory, and then open an email to me and paste, and boom, there it'll be, right? It'll be an image, and then type up what your question is. I don't understand what I'm supposed to do with this number, or whatever. Email it to me. Then I can see what you're looking at. I've been getting a few emails from people like, I'm having a lot of trouble with section 6.3. Can you help? Yeah, you want the whole lecture? What? So I need specifics by email. To work by email, I have to know, I'm working on this problem, here are the numbers, I don't know what to do now. That kind of thing. So print screen is a quick way to do that. You don't have to type out the whole question and all that. Right? Anything else over homework that's due tonight? All right, so we will jump into section 7.1. Today we'll do both 7.1 and 7.2. And 7.1 is titled An Introduction to the Central Limit Theorem. And then 7.2 is using that central limit theorem to work some probability problems. One of which is on the screen right now. So to begin this discussion, and by the way, as I always say, I will post these slides out there for you, plus all this is in the book, so don't worry about writing down every word that shows up on the screen. You won't have time. When we talk about individuals and the distribution associated with them, we can now refer to that as a probability distribution. But the idea of a distribution, we're going to look at our pulse values. Right? So when you talk about individual subjects, we refer to that as the population distribution, or the distribution of the population. Right? So for pulses, it's fairly bell-shaped and symmetric. And it's got a mean of, these numbers are going to come up in a second, but a mean of around 72 point something, and I don't remember, I'm going to get it more accurate here in a second. And then a standard deviation that was around 12, so that's about out at 84. Right? So that's the distribution of our population. Now, each of you gave me a sample of 5 pulses. Right? If I compute from your sample of 5 pulses the mean, x bar, from your sample, then I've got this number that I can compute for each of you, right? Is that statistic, remember what a statistic is, something computed from a sample, that statistic x bar, is that a random variable? Oh, what was random variable again? It's a variable that's random. Is x bar a random variable? Do you think you all got the same value for x bar? No. So that means it varies. Now, is that variability random?
Yes.
Yeah. What makes it random?
Because everybody has different heart rates.
Okay, and what makes it random?
We all pick different people.
You all pick different people. So the randomness comes in right here. If a random sample is drawn from the population, then any statistic, the mean, the proportion of smokers, the standard deviation, any statistic that you can compute is then a random variable because it comes from a random sample. And if you get a different random sample, you get a different value. So if it's a random variable, then it must also have a distribution. So population distribution is for individuals. We call the distribution for sample statistics the sampling distribution. Okay? So what we're going to learn about from the central limit theorem is what kind of distribution does it have? So let's look at our pulse values. Remember the scenario. We've got 365 total pulses that were sent to me. So we're going to treat that as if it's our whole population. And then each of you gave me a sample, really not random, you used convenient sampling, but it works for today's discussion. You gave me a sample of 5 out of that 365. See where we're going? So from those 73 different samples, I compute x bar for every one of them. So I've got 73 different values for x bar. I'm going to produce a histogram of those. Okay? Now, 73 seems like a fairly big number. That's a lot of x bars. But how many possible samples are there from 365 pulses? Remember when we were doing the binomial distribution, we learned this guy? 365, choose 5. How many ways can I choose randomly 5 things out of 365? You have a button for this on your calculator. You don't need to do it right now. I did it. It's 52 billion and some. I could take just those 365 and come up with 52 billion different random samples of size 5. So I could, if I had the rest of my life, compute an x bar for each of those 52 billion. If I graph the histogram of those 52 billion x bars, that's the sampling distribution. What values of x bar are possible, and how likely are each of those values? That's the definition of a probability distribution. It shows you what values are possible and how likely those values are. Where it's humped up, those are the values that are most likely. Where it tails off, those values are not likely. Right? So that's the sampling distribution. Here's what the graph looks like for your 73. Actually, here's what the graph looks like for all of the pulses. Right? So this is the population distribution. My little swivel thing got lost. Here is the sampling distribution. I said it again. The population distribution. Now, next slide is the distribution of the 73 pulses. All right, 73 x bars that I computed. What do you notice about this distribution compared to the last one? I like that. Brady did this. And what does that mean, Brady?
Got smaller.
it got skinnier, it got smaller, right? The spread is less. Does that make sense intuitively? That there'd be less spread in sample means than there is for individual pulses. Right? This is animation.
Get rid of the outlier.
Okay, how did it get rid of the outliers? That's exactly right. Look at this one outlier of 126. What happens when you average that value with 4 other values that aren't so extreme?
It lowers it.
It lowers it a lot. And I actually wondered, I thought, I'm going to go see what sample that 126 was in and what the mean of that sample was. And it came out of my online class, and the average from that sample was 91. And it's the biggest mean of all of our 73 means. The biggest one was 91. But that's way less extreme than 126. Right? So there's less spread. Now this doesn't look really smooth. The blue curve over the top is modeling this histogram with a normal curve. Okay? But we've got some really tall bars you wouldn't expect and some ones that are way shorter than you expect. So remember I said there's 52 billion possible samples. The true sampling distribution is of all 52 billion. We can never do that. So 73 is not close enough to 52 billion. So I thought, well, let's get a big number, but not that big. So what I did last night, I want you to know, I did this last night. I programmed on the computer to draw 10,000 random samples of size 5. It's a huge number. Nowhere near 52 billion, but it's still a huge number. And I graphed the histogram from those 10,000 random samples from among the 365. So here's that picture. Does it look normal? Looks very bell-shaped and symmetric. Right? And look where it's centered. At about 72. It's centered at the same place that the individuals, the population distribution, was centered. Well, here are the statistics. From the 365 individuals in the population distribution, the mean was 72.386. The standard deviation was 12.467. Right? Now, when I look at the 10,000 random samples, I computed 10,000 different values of X bar. Look at the mean of all 10,000 of those X bars. What do you notice? Very close. If I had the time and did all 52 billion, they'd be exactly the same. Right? Be exactly the same. What do you notice about the standard deviations?
It gets smaller because your spread also got smaller.
The spread got smaller, so the standard deviation got smaller. But guess what? The central limit theorem tells us what this value is going to be before you don't have to do 10,000 times and compute the standard deviation. You can actually do an algebraic expression. Right? It turns out that the spread of the sampling distribution is equal to the spread, sigma, of the population distribution divided by the square root of your sample size. So 12.467 divided by the square root of 5 is 5.575. From that last slide, it was 5.559. Really close. So the central limit theorem tells me how much spread I should expect in my mean when I take sample of a given size. This expression, the standard deviation of the X bars, we will call that the standard error. The standard error of a mean. Standard error of a sample mean. How much error do I expect? How much spread is there? That's what that thing is telling us. Right? Now again, it's really close but not quite perfect. But had I done all 52 billion, it would be exactly this value. Okay, so here's the central limit theorem. The reason it's called the central limit theorem is because it's central to you passing this class. Not really, but I mean really it is central to you passing it. It's not why they called it that. It's called the central limit theorem because it's centering, it's telling you where this distribution is centering, and then the word limit comes from the sample size. As the sample size gets bigger and bigger and bigger, what's the limiting distribution? Right? So we'll talk about that. So it says, for any given population with mean mu and standard deviation sigma, a sampling distribution of sample means will have the following three characteristics. If, and here's the if part, right? In mathematics, a theorem is a logical if-then statement. If this is true, then this must be true. So here's the if part. If either the sample size n is at least 30 or the population is normally distributed. What about our pulses? Do we meet the if part of this? We meet the normally distributed part. We don't meet the n equal 30 part because we took n's of size 5. Right? But you don't have to meet them both. You just have to meet one of them. So that tells us the mean of the sampling distribution of the sample means is equal to the mean of the population. That's what we saw. They both were 72 point something. Right? So the mean of the samples is equal to the mean of the individuals. Why is that important? So you need to learn to think like a statistician. I know that's scary. Think like a statistician. When I see that, I think, woohoo! Thank God. Because it tells me when I draw a sample, why am I drawing a sample? Because I want to estimate the mean of the population. So when I use my sample to estimate the mean of the population, I'm going to get it right, on average. I won't get it exactly right with any one sample, but on average, it'll be close. It's an unbiased estimate. So that's characteristic number 1. Characteristic number 2, the standard deviation, the amount of spread in the sampling distribution, which we'll call the standard error, is the standard deviation of the population. So this is individual spread divided by the square root of the sample size. Okay? Now here's another think like a statistician. When you look at that, what does it tell you about sample size? If I make n get bigger, what happens to that?
Standard error gets smaller.
Standard error gets smaller. Why?
Because you're dividing by a larger number.
Because it's on the bottom of a fraction. You divide by a larger number, you get a smaller number back. So what this says in layman's English is big samples, good. Small samples, bad. The bigger your sample is, the less error you have in your estimate. This is the standard amount of error you would expect when you take a sample of a certain size. You want small error. So take big samples. Now we learned from that one example back in chapter whatever that big samples aren't always good. So they have to be random, unbiased samples. But as long as they're biased, as long as they're unbiased and random, bigger samples will give you more accurate estimates. The shape of the sampling distribution is the third characteristic. What does this say? The shape of the sampling distribution will approach that of a normal distribution, regardless of the shape of the population distribution. So here we have pulses that are normally distributed to start with. But even if it was horribly skewed, as long as you have at least 30 in your sample, the shape of the sampling distribution will be very normal. Now why does that matter? Well, it lets me compute probabilities of things. Right? If I design an elevator, and this elevator is designed to take a total amount of weight, and I can say, well, what if 10 people get on this elevator? What's the probability that the average weight of those 10 people will be above my limit? Well, if I can approximate that with a normal distribution, I can compute that probability and say, well, how likely is that to happen? Not very likely. Or if it's fairly likely, maybe I need a stronger elevator. Okay, so here is a histogram, the population distribution of pulses once I pooled this semester's data with all my past semester's data. So I'm actually up to almost 10,000 observations. So you guys had 365 pulses, but all the semesters I've been doing this, I'm up to about 10,000. Right? So here's the histogram. It's very bell-shaped and symmetric, but it's not perfect. Right? It's a little bit skewed. It peaks a little too soon, and then this tail's a little too long. Right? So there's a slight amount of skew to this distribution. But we'll see the central limit theorem still works very well, as long as it's reasonably bell-shaped and symmetric. Here is the sampling distribution using samples of size 5. It's like the one we saw before. It's centered at about the same place, and it has the spread according to that formula. Now, when I hit page down, I will have the picture for samples of size 10. Instead of n equal 5, it'll be n equal 10. What's that picture going to look like? You even did a sound effect. It'll shrink it. It'll have less spread. Now what about the height of it? It's got to get taller. Why has it got to get taller? Okay, what's the total area under the curve? 1. So if you squish it in, it's got to squirt up. Those are statistical terms. Squish it in, it's got to squirt up, right? So here it is. Now, it doesn't look like it squirted up, but I didn't think about it until it was too late. To control the axis, this one's at 25. The one before was at 17 something. So now look at where 17 is, about right there. It did get taller.
But your x-axis has been staying the same the whole time.
Yeah, I did think to keep the x-axis the same. Right? Now, if I take samples of size 30, again, the y-axis changed, but it gets skinnier. Right? So here we go, all the way. Individuals, 5, 10, 30. And if I didn't keep going, but I could keep going, sample size 50, 100, samples of size 1,000. If I had samples of size 1,000, the standard error would be so small, it would be pretty much one spike. You wouldn't expect to get a mean from 1,000 pulses that's more than 1 beat per minute off from what the true mean is. The standard error gets so small that you can be very confident that you got it almost exactly right. But if you take samples of size 5, there's a pretty good chance you're going to be off by 5 beats either way. Right? So big samples, good. Now, what about age? Very skewed distribution. When I took your 73 samples of 5 ages and compute the mean from each of those 73 and then do a histogram of those, what's it going to look like? Okay, so you're thinking it's still not going to be normally distributed? Okay. What does the central limit theorem tell us will happen?
If you have a sample size of 30 or more, then it will take normally distributed.
If you have a sample size of 30 or more, it'll look normally distributed, regardless of the shape of the population distribution. But we got samples of size 5, so we're not going to be normally distributed. So let's look and see what it does look like. It's actually not that bad, but it's clearly skewed, right? This is much steeper, and it goes longer tail over here. So I would not trust using the normal CDF function on my calculator to compute probabilities here, because it's not a really good model of it. But if I go to size 10, samples of size 10, it's not too bad. It's still, you can see some skewness to it. But it's not really that bad.
So is your program just taking 10 random
Yep.
Mosier distribution?
Yep. It's just randomly, it's picking random samples of size 10. Now, if I go to 30, then it looks very bell-shaped and symmetric. So that's the if part of the central limit theorem. If you have samples of at least 30, it'll be normally distributed, even when the original data is not normally distributed. So now I would trust computing probabilities. What's the probability? I could take a random sample of 30 individuals, and I'd get a mean age in a certain range. I could use my normal CDF function to answer that question. Right? Because the central limit theorem has, as I say, kicked in. Right? Sample size 5, not good enough. But by 30, then it's close enough to its limiting distribution of normal distribution. All right, so here's a type of question you're going to have to answer over this homework, section 7.1. Suppose that the standard deviation of movie ticket prices in the United States was 72 cents. Oh, I thought 72 cents, what is this, 1930? But that's standard deviation, that's not the mean, right? Do they tell us the mean? No, they don't ever tell us the mean. They just tell us the standard deviation. So standard deviation is 72 cents. All right? Suppose means are calculated for samples of size 52. That is, ticket prices are recorded for different samples of 52 theaters, and the sample means are calculated. What would the standard deviation of the sampling distribution be? That is, the standard error of the mean. So compute the standard error of the mean from samples of size 52. Remember what the formula is for the standard error of x bar? The book writes that as sigma sub x bar, and I will too sometimes, but I tend to write it out like this, SE of x bar, just because I can remember what that is, standard error of x bar. How do I compute it?
The 0.72 divided by the square root.
Okay, good. So it'd be sigma over the square root of n, which is 0.72 over the square root of 52. And what's that number? 0.0998.
Yep.
Like that? Okay. I think that's even on the next slide. Yep, there it is. 0.0998. Okay? So the sampling distribution would have a standard error of around 10 cents. So individual movie prices have variability of 72 cents, but samples of 52 theaters would have variability of only 10 cents. Okay? Here's weights of horse jockeys. Skewed distribution. Can the central limit theorem be applied to the sampling distribution if we take samples of size 45? Yes, because you've satisfied one of the two or parts. Right? What is the sampling distribution's mean? I got to scroll back to the previous page. It says the mean of the population is 116.2. What would the mean of the sampling distribution for samples of 45 jockeys be? What's that?
Around 100.
It'd be 116.2. Yeah. So the mean of the sampling distribution is exactly equal to the mean of the population. Now, when you took a sample, you'd get a number close to that. So when she said it'd be around that, but this is talking about the center of the sampling distribution, which is all possible samples. Right? Now, the next question is, what is the standard deviation of the sampling distribution? What is the sampling distribution's standard deviation? So what do? This is not set up well for me to keep scrolling back and forth, but does anybody remember what the standard deviation was for the jockeys, individual jockeys? 3.9. So what's this going to be? It'd be 3.9 divided by square root of 45. And what did you say that number is? 0.1592.
No,
That's right.
0.5814.
Okay. I'm getting a
It's 0.5.
disagreement. I better write it down. What did you say? Point what?
5814.
5814. Okay. Part D. What is the sampling distribution's shape?
You would.
Normal.
It'll be normal. The individual jockey's weight was skewed, but this has samples of more than 30, so it'll have a normal distribution. All right? Okay, let's jump to section 7.2, which is applying this to
Wait, did we get
probability problems.
the third characteristic?
Yeah, shape.
Oh, I just.
Yeah, third characteristic is just shape. Okay, we won't have to do much with these z-scores because we got the calculators that will compute it automatically. However, some of the homework problems are probably going to make you compute a z-score. Same as it always is. You take the mean, you subtract, you take the value you're interested in, you subtract the mean, and you divide by the standard deviation. But now it's of a statistic, x bar, so you've got the sample mean minus the mean of all possible sample means, which is the population mean, divided by standard error. Right? So the z-score now is z equal the sample mean value you're interested in minus population mean divided by standard error of the mean. Right? So written a little bit different way, notation-wise, that's how you're going to compute z-scores. So some of the homework problems will say, what would the z-score be for this? But then, as I keep saying, they're going to then try to walk you through converting values into z-scores and then using the normal tables in the back of the book. You don't have to do any of that. You can go right to your calculator. So let's see the kinds of probability problems. Okay, here's a question. According to the Centers for Disease Control and Prevention, the mean total cholesterol level for persons 20 years of age or older was 197. Okay, wait, I need to organize information because this is too much all at once. So the mean of the population of cholesterols is 197. Right? That's what they're telling me. And the standard deviation is 35. So I write mu sub x, no bar on the x. No bar on the x means individuals. So this is population distribution. Okay? What is the probability that a randomly selected adult from the population will have a total cholesterol level of less than 183? Work that problem. It says, assume the cholesterol levels are normally distributed. So in mathematical symbols, they say probability that x is less than 183. No bar on the x. It's an individual adult. If we randomly selected an adult, it's not a sample of adults, it's one adult. So compute that probability. Now I'm going to come around and look at your answers. Give you a hint. You have homework due tonight that is just like this. So this problem is talking about individuals. This is out of chapter 6. Yep. Normal CDA. Inverse norm is when they give you a probability and want a value. Here they gave us a value of 183 and they want a probability. Where's your calculator? Some people. Oh, I should have said that. Oh, you got an extra one? You guys know what to put in? Nope, you're almost right. So negative infinity
Sounds like-
up to 83, but then you need the mean and then the standard deviation. You got an answer? Okay, that's right. That's not right. Oh, you put 135 instead of 35.
Oh.
4 decimal places. You got an answer? Okay, good, that's right. Okay, you guys all matching? Okay, what'd you get? Good, right? Got it? Yes, I got it. What'd you get? 3, 4, 2. That's it. Is that what you got? Right. Rachel?
Like the last time I visited my community.
Okay, looks like most of you are. I think this is like the Exorcist. I'm going to twist her head off. She won't come.
Go the other way.
Oh, what's her?
Follow me. Okay, so normal CDF. It's for an individual. So it's normal CDF from what to what?
Negative.
Negative infinity, because there's no lower bound, up to 183, then enter the mean and the standard deviation. Right? You don't have to convert to z-scores or do any of that stuff. Right? Now, I'll page down, and it will want to know the probability that a randomly selected sample of 150 adults from the population will have a mean total cholesterol level of less than 183. Work that. And I want you to go through the step. I know most of you didn't the last time, but I'll go through the step of getting a ballpark estimate. And just like it's going to be really small, it's going to be kind of medium, or it's going to be really big. Really big probability. This time I'm going to leave this behind. You still read that? It sounds like it's almost the same question, doesn't it? What's different? It's the probability of a mean from a sample of 150 people being less than 183. So, how do I write that, this equivalent type expression? What do I write? Probability of what?
X bar being less than 183.
X bar being less than 183. This one's X, this one's X bar. Okay? So now work that. Hint, you'll have to use the central limit there. Let's see, I'll start on this side of the room this time. What are you going to do? Okay, you can draw something to get your, and in order to draw it accurately, you need to know what's the spread going to be, right? So what is the spread going to be? Central limit there. What does it tell us about this number won't be right anymore?
That's what I got, but I don't know if that's right.
35? I can't use a 35. What do I need?
I just converted.
35 divided by, this part is right, but up here
And then
you
I just
put the
put my
last
circle in,
probability.
But
The last probability.
to find the west side.
Yes, so I mean, I only changed one number in there.
But you plugged into this equation where this is 183. Or is it
Okay, good, that's right.
where's that?
No, I didn't change that one. I plugged into that one. But I'm not entirely sure that.
Mu is always the same exact mean. There's a standard deviation that changes. Okay, you're real close. It looks like you're trying to do this equal. You don't really have to do that. But you put in it. This is in. You don't want in, you want mu. Right?
Because it's
Oh, yeah.
shallow.
Okay. The central limit here tells us that as long as we have a big sample, that the distribution of x bar would be normally distributed. So you're going to do normal CDF. Right? Normally distributed. What's different? Okay, now lower bound, it says x bar less than 183. So lower bound is still negative infinity. So you're good there. And then the upper bound of the region is 183.
I don't think that.
Now what's the mean? The mean of the sampling distribution is the same as the mean of the population. It's going to be 197. Now the standard deviation is what's
Fine now.
triggered.
It's fine now.
That's sigma over the square root of n. Remember? Okay?
Right.
All right, so this one's a little, people are struggling a little more with this, but the central limit theorem tells us this thing is normally distributed. As long as I know that, then I'm going to compute probabilities with my normal CDF function. So just knowing characteristic number 3, the shape of the distribution tells me, oh, this is a normal CDF problem. Now my lower bound and my upper bound are the same as they were here. Negative infinity to 183. What about the mean?
It's the same.
It's the same. Central limit theorem says, that's characteristic number 1, that the mean of the sampling distribution will be the same as the mean for individuals. What about this?
2.8577.
Okay, and you got that by,
Second part of the central.
you take the standard deviation of the population and divide by
And your population
the square root of the sample size. Right? So, and you can enter it right into your calculator directly, and I recommend you do that. Type in 35 slash square root of 150. Then you don't have to have, then you won't have round off error from having computed this and then typed it into 3 decimal places or whatever. Right? This is the most accurate way to do it. Plus it saves you a step. Yeah?
Where'd you get 197?
Right here. The mean of x bar will be the same as the mean for the population. That's the central limit there. So I know I'm going to use the same exact mean that I had for individuals. Okay? And then the standard error is what changes. So everything is identical. Now, Ball, I didn't have you draw the picture, but what do you get as an answer here? Okay, you got,
Like 4.824 to
okay, so 4.824, right? Now, I want you to pay attention to this. I want you to look around the room, and somebody sitting in here right now, on the test next Friday, will write an answer like that down and go on to the next problem. But if you take 5 seconds and go, does that look about right? You think, oh wait, I'm computing a probability. Probabilities can't be 4 point something. Probabilities must be between what and what?
0 and 1.
0 and 1. So then you realize, oh, you grab your calculator and you look and see if you've missed an E minus something out there to the right side. So you can write your answer, full credit on the test, as E minus 7. But don't forget that part. Or you can actually move the decimal 7 places and you get 0, 0, 0, 0, 6 zeros, and then a 4.
Did you guys
What? No.
I'm here.
Yeah, I'll mark them down. I have a good memory for about 30 seconds. I'll get it down. All right, we'll see you Monday. Have a great weekend. Root for the Royals today.